Hello, y'all. Daryl Lee Berry doing it back with some more quantum mechanics as promised. And we'll continue with what we started earlier. I still have my background up with the Frank Hertz experiment, where you can see the quantum effects of the quantum reality of particles and the way uh, the different data shows up in the light, like I mentioned in the first, at least the previous section of this. So I'll actually start with a correction. I noticed that I was looking at this nitrogen one incorrectly because I was looking at the uh, L calculation incorrectly. So when we're doing a term symbol here, this is the L total. So the big L is basically L total, which is not necessarily the same thing as the L in the configuration. So in this one, we can see that L, the L total equals big L is ML1 plus ML2 plus ML3. And in this case, we're talking about nitrogen, all three of those um, places in the p orbital are filled to add up to 0. So big L equals 0, which is the S state. So this is actually a quadruple S term symbol with 3 over 2 for J. So I noticed that when looking over my professor's lectures earlier. So let me take a quick look and make sure if I didn't make that mistake before again. So L equals 0, we have S. L equals 0, L equals 0, S. If it's full, then it's just the default. L equals 1. So P, so hold up. So here L is 1. That's right. Here L is 1 because we can see that these are going in the same direction. So I'm still slightly confused on the addition, I think, but enough to get a fair amount of points. But it's just important to recognize that the sum of the L's. So I guess one way to look at this, Professor was saying that we have to maximize the L's when we get to this point. So here is the S configuration, so I just have one of these, and one of those is here. So there's no vector. ML equals 0. So this L is 0. There's no M's to add. Here is full, so we get the default. Here little L equals 0. ML equals 0. So L equals 0. Here, default. Here, so little L equals 1. So ML equals -1, 0, or 1. And we have just one of these. So this is where it seems we can have some differentiation. So spin is just S. So this is where I was thinking about it incorrectly. No, the really little L is 1. So I have 3 of these. But we want to maximize the L's. So if we're going to maximize the L's, we would do L equals 1 or ML equals 1. Thus L equals 1. So this would still work. So maximizing the L's. So one key is to maximize the L's. Hey, what's going on, Wilfredo? Awesome, Wilfredo. Thank you for dropping a line and let me know you appreciate it. So that definitely motivates me to continue when I have some feedback and some appreciation. So thanks for that. And if you have any questions, let me know. Oh, and I'm not a doctor yet, by the way. I anticipate I'll be a doctor in 5, 6 years. I'll be starting graduate school in the fall. I'll actually do a reveal video um sometime this month and share where I'm going. So I'll make a nice little reveal video about it, let you know where I'm going, a little bit about the school to earn my PhD. After I make sure I pass this class, this is the last exam I have to do is Quantum 2. And as long as I do well on this exam, even moderately well, I'll pass the class and I'll be on to graduate school. And looking at this, we have, so maximizing the L's. And what I'll do is I'll move this a bit. If I'm going to call this as it is, I will call the left one -1, the middle one 0, and the right one 1. Uh, then that's why we put that electron, the valence electron there to maximize the L. So I have to remember that detail that I learned from you watching the professor's explanation of this process. So L equals 1, then should actually just be 1 thinking about it. At least 1/2 that is, like just positive. There's only one electron there. So I'm thinking probably should be like this. Here we have 2 in the outer shell, 2 electrons. So we still want to maximize. But I suppose what I did here works if you want to count every single possibility. But maximizing it is going to be this one. And here, same thing. This is a P configuration. So the P configuration lets us know that we have 3 places to put electrons, 6 altogether, and 1 up and 1 down spin. But as I learned and reiterated from rewatching the description of this, of the lecture of this from a professor, the electron. So once we put the first electron there, or once nature puts the first electron there, that electron has a magnetic moment. It's like a little magnet in a sense. So when we put the another electron to build up that atom, the second electron wants to align with the first electron. That reminds me how from chemistry we always stack in the same direction. Like we don't like put the second electron like this upside down. We stack in the same direction, and we learn from quantum mechanics is because the spin mechanisms in the particles, or the angular momentum, the magnetic dipoles, all of this stuff reacts a certain way. And specifically, the dipole of the first electron has an impact on the second electron, so it wants to be aligned with it. It's like how a compass aligns with the magnetic field, and thus we have those in line. So that's why we have ML plus ML equals big L, which is 1, because it's a half and a half, because the spin is 1/2 for each. So we have the S is 1, we have the all the so this is the detail I missed that I caught from my professor's video. Uh, Let me actually start this one again. Well, not maybe I don't have to start the whole thing again. It's just to do with these L's. So notice what he did was he took these MLs. So each of these are sub-levels of the uh, L equals 1 state, which is the P configuration. And he treated these as if they're vectors. Like this is the ML equals 1 vector, and this is the ML equals 0 vector. And the vector, the big L vector, is basically adding these two together, vector addition. And I'll pull up those notes to make sure I don't make an oversight. So see if I can round out a detail that may save me a few points on tomorrow. So yeah, so he's doing, okay, maximize it. So like in this case, ml equals 1, ml equals 0, and he's actually doing carbon. So that's probably what made me stop here to rethink this one, because that's the one I was watching. So I add up the ml equals 1, which to keep the color coding is this one. The ml equals 0, which is this one. And when I add these up, I get the L equals 1, which is the L total with the addition of 2 electrons in the p orbital configuration. So this is why my L equals 1, which I did have here, but I didn't fully understand it, which I'm sure I still don't fully understand it, but I understand it a bit better now. And this is what gives us the 3 possibilities here from adding up these 3 different MLs. Now, apparently we need to maximize the value of L. So this is the order that will, I imagine, happen uh, most probabilistically in nature. But it's also possible to do the +1 -1 Now, why is it that I have 2 from the spin? So this, I wrote this in reverse is what I did. So I don't think it necessarily matters, but to make sure it matches, spin is on the left, and the spins add up to 1 because, as I said earlier, these two electrons are wanting to align in the same direction, like how compasses align. It just so happens that the electron is the other's electric or magnetic field that makes it want to align. So they align in the same direction. And that S can be added to either combination of those 3 MLs to get the different potential J's we can get. So when we're looking at the term symbol, we have the 2s plus 1, which will give us the singlet, doublet, triplet state. So since spin is 1, since they're aligning in the same direction, that's 3. So this is a triplet state. You can see the 3. That's what this means. That's something, another new detail that I picked up as well. That this is exactly what they're talking about when they're talking about whether a state is singlet, triplet, how these angular momentum properties, you know, are coupled together and sum, and what we get, right? The resulting J, or the resulting total orbital and spin angular momentum that we get together. So this is a triplet state, and with all the different ML combinations, we have a triplet state. Now, L, I've confirmed is 1, so it is P, and no, hold up. So this is where, yeah, does he have P? Yeah, he does have P. He has triplet P. So this works. And let me see, let me confirm I didn't mix it up with N. So we do have the S total is the S1 plus S2 plus S3. That is 3/2. Now, one different thing is uh, when he added these 3 together, he literally added all 3. So it'll be each of these 3 added together, -1, 0, 1. So they actually add up to 0, ironically. So let's see here. So L is 0. I have that here. And because L is 0, I end up with S for the term symbol state. We end up with a quadruplet, and 0 plus 3/2 for the spin. So you end up with a quadruplet S 3/2 term symbol. So I am getting better at this. That's for nitrogen. For oxygen, and this is the one he's doing now. So you end up with this. And these are the unpaired electrons. So 2 of them cancel out. So S is 1. L, when I add up just the free ones together, we have ML equals 1, ML equals 0. We're going to maximize L. So this will be big L equals 1. Let's see if he gets that. Yep, big L equals 1. That's Y. So this is a P state in the term symbol. And Now, he actually has, let's see, 2s plus 1, s is 1. Have a triplet. He seems to have a quadruplet. Oh, no, I'm sorry. That was the configuration I'm looking at. He didn't get to the term symbol yet. So yes, 2p4 is the configuration. Let's see if he gets 3p2 as well. So he does have the triplet p because L is 1 for the term symbol. And he has 0, 1, or 2. So he does the thing where he alternates which one these are. Whether it's 1, 0, 1, -1, or 0, -1. All right? And that'll determine whether L is 0, 1, or 2. To me, J is 0, 1, or 2. L is going to always be 1. So if, to me, S is going to always be 1. So if J is 0, it's going to be if L is 0, J is 1. If L is -1, J is 0. And if L is 1, J is 2. I think I said that right. So what we're about to do now is fluoride. And I'll try this one and see if I get it correctly. And those who are watching, be sure to subscribe if you haven't. Help me get to 1,000 subscribers. So what we have now is fluorine. And it's written kind of horribly in the way the program he's using didn't quite carry over the mathematic notation. So, and fluorine is just F. It has, out of 60 electrons, it has 5. Out of 60 electrons, it can have any p orbital. So it has 1 S2, 2 S2, and 2 P5. Good. So I'm able to understand the periodic table better as well. Perhaps I can clarify that for you all. Let's pull up the periodic table here. So this is our periodic table. Maybe I shall rename this. So looking at the periodic table here, we can see that the it shaped something like this. Here, it takes this part out and puts it here. Now, if we look at this, we see that this one has two columns. We see 2, 4, 6, 8, 10 columns in the middle. We see this one has 6 columns, so 6 columns here. And here we have 3, 6, 9, 12, 15 columns. And this relates directly to the fact that if you have a not a term symbol, but a configuration symbol of S, that's L equals 0. So you have one place to put up to, one orbital to put up to 2 electrons. That's the 2 columns. So this uh, um, column has 1 electron. This one has a filled electron outer shell. And let me make sure I have that correctly. I know that the neon, yeah, I think that's correct. It's just helium is a bit different because helium is way over here because it is a noble gas, is my understanding what they call those. Um, but even so, it still has 2 with the, you know, hydrogen has 1, helium has 2 in the S state. The P is L equals 1. So ML equals -1, 0, 1. That's how we have 3 different places to put up to 6 electrons. And that's why we have the 6 columns here. Right? So basically each one of those is another electron. Boron, for instance, the one that's right here, boron is atomic number 5. It has 5 protons, so it must have 5 electrons to balance those. Carbon has 6, it has 1 more. So each one of these elements have an extra electron in the p orbital, and those are the 6 columns there. The middle 10 is the D, I guess I should say D uh, configuration. L equals 2. So we have ML equals -2, -1, 0, 1, 0. So we have 5 places that can hold 2 electrons each, 1 up, 1 down. As you can see, we have 10 electrons total, and that's why we have the middle part of the periodic table having those 10 in red. And I realize y'all are not seeing my writing as well. And I'll turn this way. So y'all are able to see with the actual periodic table up, we saw how the 2 column ones is the S, the 6 column ones is the P, the 10 column ones in red is the D, and technically some of those is green in the um, 6 column one, the p orbital. And when we see these sort of brown pink ones down here, so this will be the F configuration where L equals 3. We have ML equals -3, -2, -1, 0, 1, 2, 3. And these 1, 2, 3, 4, 5, 6, 7, each of those can have two electrons, one spin up, one spin down. They can't be in the same state because they're fermions, like we talked about in my thermodynamics class. And as you can see, we have 14, and thus we have 14 columns here. 3, 6, 9, 12, no, counting 15. All right, so there's something different about this, and something vaguely is starting to come back to mind about some, well, no, that shouldn't be the number of electrons. I was thinking about how one of these exclusion principles or something, how in certain elements at certain parts of the table is actually lower energy to fill a higher orbital first. So instead of going like this straight across all the way and then coming down the other way, like one of them goes the other way first or something like that. I don't remember exactly. Am I counting this right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. No, it is 15. I don't know why how I was counting an extra one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, yeah. So the exclusion thing shouldn't affect the total number of electrons in the orbital. It just affects the order at which the orbital is filled. But we do see that we have, but no, no, it still only have 14. I don't know where the extra one is coming from. We have 14 spots with 15 columns. Yeah, I don't know about that one. So maybe our chemist to have to, or maybe I'll learn about it in graduate school, why that one has an extra column or a column difference. With the ones that we utilize in class now, in the undergraduate level of physics at least, uh, we mostly deal with S and P. Talk about D sometimes, but most of our calculations, as you can see, and what we're doing right now is S and P. Now, but right now we're trying to do this fluorine. So as we discussed, the fluorine is in a P configuration. You can see fluorine right here on the right side over here. It looks like you can see my mouse on the screen. So we're dealing with, and I feel the need to copy this down and just start our first page. So we're dealing with the configuration L equals little l equals 1. So ML equals 0, so 0, 1, -1. So we have 3 places to put 6 atoms. We have some electrons. We have 5. We can see right there. So we know it's going to fill in the same direction first because of their magnetic moments. Are going to want them to align. We have 2 down. That gives us our 5. So we have just 1 free electron. So that should give us a S equals 1/2. And if S equals 1/2, we'll probably want to maximize the mLs. So we'll probably want to use the mL equals 1, 1, which will make big L equal 1. And that'll make the J equals S plus minus L. So that's going to be 3 over 2 and 1 over 2. So I guess the L does go first. So if I'm understanding this properly, since L is still 1 for the term symbol, it will still give me a P for the term symbol. 2S plus 1 equals 2. 1/2 plus 1, that's 1, so that's 2. So this would be a doublet state, and J is 1/2. So let me take a look and see if I got this one right in the lecture. So this is one that he wanted us to do for our in-class problem. So, and thanks those who are watching. Be sure to like, share, subscribe, all that good stuff. Help me get to 1,000 subscribers. And let me know if you have any questions. You can drop a line right in the live chat. So the S is asking for the S, L, and J values. So I will say 1/2, 1, and 1/2 or 3/2. And that does ring a bell. Let me see what they say the answer is. Yes, I got it. I got it right. All right, guys. So why don't we look at a few other questions since I was able to get that one. To keep 1/2 or 3/2, maximizing the L state. So the next problem deals with the fact that transitions are allowed to happen in certain ways. So we have a helium atom and its initial level is the triplet S, and the final level is the singlet S. The way these transitions, like these transitions of energy, happen with the electrons in the atom, the change in S has to be 0. So it can't change spin, which makes sense because the electron just has its spin, and when those things mix up, is just what it is. But the L should change by plus or minus 1. So when we look at a helium that its initial state is the triplet S state and its final state is the singlet S, we see that S did not change, so that's false. And we see that L changed by 2, because remember from our term symbol understanding that the it's going to be L, J, and 2S plus 1. So 2S plus 1 equals 3. 2S equals 2. So S equals 1 initially. 2S plus 1 equals 1. 2S equals 0. So S equals 0. Did I calculate that wrong? Oh, yeah, that's right. So it changed by 1. That's not supposed to change. I was mixing up which one is supposed to change or not. So it changed by 1 is wasn't supposed to change. The S changed by 1. And the L did not change when it's supposed to change. So this is false. So this means that this is a unallowed transition. And that's why the A factor, which is 1 over S, is basically 1 times 10 to the negative 4. 1 over S. Which means when I divide that, it's going to be a very big number. So it takes a long time for this transition to happen. So what that means is in nature, even though we are aware that there is a transition in helium uh, between these levels, the wavelength of the transition is 62.56 nanometers. It happens very rarely because of the leap in uh, S state that does happen, and the lack of leap in the L state. It is not a favorable transition. Um, for calcium, I believe that's calcium, it goes from initially the singlet P state to the singlet S state. Remember that change in S has to be 0 and change in L has to be plus or minus 1. So we see that the S does not change, so that's true, because we see that it's a singlet on both sides. And we see that the L does change by 1. It goes from P to S, which is L equals 1 to L equals 0. So that's true. So this is an allowable transition. we see that the A factor is roughly 2 times 10 to the 8, 1 over seconds. So when we invert that, time equals 1 over 8, that's going to be a very small amount of time. So these happen pretty often. And the last one, oxygen, we have an initial state, a singlet S big L orbital. The final state is a singlet big D. So now the first thing we notice is this changes by 2. So remember that the change in S needs to be 0. The change in L needs to be plus or minus 1. So it does change in L, but it changes by 2. Because S is L equals 0, P is L equals 1, and D is L equals 2. So it changed by 2, so that's not favorable. But the S's don't change because we can see that the superscript, because remember that superscript is 2S plus 1. So S remains 0 because 2S plus 2 times 0 plus 1 is 1. So it's half favorable. And if you look at the A factor on this one, A is about 1. So this happens in between those two, which makes sense. So this one is completely allowable. Therefore, it happens very often. This one, the 1 is true, but the other is false. So it's in the middle. And this one, both of them are false, so it takes a long time to happen. And let me get a drink of water before I look at these last two problems. So I'll put a be right back in case anyone pops up. Be right back. Right. So last two things, I'll make this quick. Another problem we had was looking at uh, trial wave functions and having to identify which is the good and bad ones. So if we look at this function here, and let me go back to the big screen since we don't need the periodic table anymore. Right. So basically, this is a trial wave function for the variational treatment of helium. And N is a constant to normalize it. A and B are the spin up and spin down states of one electron. This is helium, so we have two electrons. So A is one electron, B is another electron. And this is a trial wave function to um, try to demonstrate some of the properties of, I guess, quantify some of the properties of the helium atom, sort of modeling it as a space part and an orbital part. And what makes this a good state is two things have to happen. If I were to swap, and actually I'll go ahead and do that. So I have it written out. So if I were to swap R1 and R2 everywhere I see them, and if I were to swap 1 and 2 everywhere I see them, if we compare these two equations, for one, we notice that these two are the same, these two here. Now, they're in the same, in different positions. Like for instance, this equals this now, and this equals this, if you look at it, right? They're the same exact thing. So that's the first thing that has to happen is if I change so basically R1 and R2 is basically the distance to either uh, nucleus, from recalling property, at least the nucleus to the other electron. Uh, and this is helium. So we have 2 protons, 2 electrons. And this factor here, as it was saying, are the spin up and spin downs of either electron. But notice this changes the sign. So notice here for the top one, the A2B1 is negative, but here the A2B1 is positive. So we see that everything stays the same except the sign swap. So the fact that I can change R1 and R2 and 1 and 2 for the electrons, which electrons and everything stays the same, but the sign swaps, that's all that changes, that makes it a good state. So if I have an equation to where if I swap R1 and R2, it becomes a different equation, then that's not a good equation. And if I swap 1 and 2 for the electrons and the sign doesn't change, then that's not a good acceptable variational treatment. So basically, it's like a simplified way, since we can't technically calculate the helium details correctly directly, because we can't even do a three-body problem still. Like we can't properly, for instance, calculate the orbit of 3 stars around each other. So we definitely won't be able to do it with 2 protons and 2 electrons. What we can do is sort of approximate helium as 2 hydrogen atoms, and this is sort of what the variational principle does, if I'm understanding it correctly. And the last problem I'll talk about is basically, well, actually, there's two. Hold up. One is the variational equation. So this is the direct integral. It's a double integral. I have psi what S R1 through over R1 2 and psi in L squared R2 D3 R1 D3 R2. And this is the direct integral. And it says the multi-electron atom, so this will be D2, which means that and let me make sure I'm clear on which one it is. I'll take a look at the actual file. So this is some stuff that I went over earlier. By the way, I had organized a study group. Only one person came to this one. We were each able to help each other on this or that. Like I helped him with um, determining the symmetry of a particle in a two-dimensional well, using integrals and a few other things, and he helped me with a few things as well, including this. So this integral here is the direct term for electron. So this is electron directly, which makes sense. It's direct. Cross terms would be electron to proton. So electron to proton is exchange, how these forces exchange between, let's say, one part of the uh, hydrogen 2 atom, hydrogen plus to the other. I guess technically H2 plus helium plus. So technically that's it. Like we had a helium with, technically that's a helium with one electron. So this is for a regular helium atom where you have a proton, and an electron. And these two electrons are going to be interacting with each other, and this direct integral carries that out. There's also a cross term, x2 equals some constant. Looks like that one didn't put a constant there, but I'll go ahead and put a constant there. A constant double integral psi naught r1 psi naught r prime 1 over r12 psi naught r2 psi naught r prime 2 and d3r1 d3r2 for integral over a volume. So this exchange term is basically the electron to the other proton. I guess the electron with the proton um, farthest away from it. So basically we just had to write this formula down and explain what it meant, which I need to work on that part beyond what I told y'all just now, right? So the last one, last one is basically an understanding that if we have a helium atom, for instance, we end up having an equivalent of particle in two wells, like we talked about infinite wells and finite wells and things like that, and it seems sort of hypothetical. But when you actually take electrons and put them near protons, the protons act like wells, like gravity wells, but it's really a electric force type wells and angular spin and other type of stuff wells. So basically what's going on here is like we talked about before, these electrons will be repelling each other, so that the direct term will take care of that. But these protons will be pulling on each electron, so thus we have these exchange terms going on. And what happens is these forces together, the attraction between the electrons and protons and the repulsion between the electrons, they balance each other out and gives us the distance that occurs in nature between the protons of a helium atom and the electrons, all of these things, so they're fit configured. So basically, if we take and draw this as a plot, now let's say I have energy on the y-axis, energy as a function of radius, and I have radius on the x-axis. Now let's say the radius is the distance between these two protons. What happens is we end up with a potential that looks something like this. So if the radius is very big, meaning over here the protons are very far away from each other, Well, what happens is the dominant force is going to be the attraction between the electrons. So the electrons will be um, repelling from each other but attracted to each other's proton, but it'll result in a higher energy because this tug of war is going on between these two very far away. The protons are not really getting evolved as much, but this electron is very closely attracted to this proton, but it is still somewhat attracted to that proton. And the same thing, this electron is very attracted to that proton, but it's still somewhat attracted to that proton. And but the push between the protons is not that strong because they're so far away. So uh the two nuclei will tend to want to get closer. The electrons will win out in that case. Now let's say we're on the other end where the protons are very, very close to each other. This aura is very small, or the electrons are there, but even though the charge is between the electrons and the protons are roughly the same, still these protons are so close together that they really want to push each other away. They really is pushing each other away. Is very hard to keep them close, takes a lot of energy to keep them close. So this would be another high energy situation where you'll find in nature that particles want to get where the energy is lower, where it can relax, where things are copacetic. So you put protons really close to each other, you'll find they'll want to repel. So if they're very, very far away, they'll sort of attract towards each other. If they're very, very close, so they're very, very far away, will want to attract to each other. They're very, very close, they'll want to push away. Now, there's a certain distance, a certain range at which the direct repulsion of the electrons and the direct cross attraction of the electrons and protons balance, and this ends up being the bond length. So the bond length between the particles in one atom or between multiple atoms, like in water, if you have H2O, the bond length is determined where this balance happens, where they're close enough to each other to where the electrons feel a good attraction to the protons, but they're far enough away where the protons are not going to kick each other away from each other. Hey, what's going on, Catherine? And Catherine says, "Hi, I didn't get your notice. How was the exam? It was actually all right. I think I did well. Uh, uh, the only problem that I had a problem with, which is most people had a problem with, was the last problem. Uh, Basically, what he asked us was, um, which was right along the lines that we're talking about here, as a matter of fact. But he asked us the probability of a a so basically the probability of a fermion, like an electron, being in a certain state versus the probability of a boson being in a certain energy state, which is what is a boson? I think a neutron is a boson. I'm not sure what a boson. I mean, a boson is basically a particle that doesn't mind being in the same state with other particles like it. So you can put a whole bunch of bosons in the same state. But you know how earlier I was saying the electrons had to be in different configurations up and down? That's because they're fermions. So fermions have to be up and down like this. But a boson, they could just all just stack up in the same direction and they don't have a problem. So that's the difference between the fermion and the boson. But the probability, because of how they behave differently, is different. The equation, the calculator is different. So what he asked us was, at what temperature would everything else being the same, at what temperature would you need to have essentially for a boson and a fermion to behave with the similar behavior as far as getting an energy state, with this being B naught negative, which we can just call X. And it was rough. Everybody said it was rough. I got an answer. I got that the difference has to be close to zero. I don't know if it's the right answer. I had to restart a few times with the calculation. And after the exam, a few of us talked, and everybody had problems with that problem the most. So it'd be interesting. I actually did a sort of thing where he wanted it to be within 5%. So I sort of took a deal where if I have the probability of the fermion, and I added, let's say, 5%, I get the probability of the boson, and I did that calculation. And other people sort of did a probability of the fermion over the probability of a boson equaling 5% or something like that. So I think either way, and I don't know if this would be 5%, like if it was 105 and 100. I don't know if that'll be 5%. What is that? Let's see. I don't know. I don't even know what that comes up to. Uh, so 100 divided by 105, 95%. So some people did it that way. I did it the first way. I guess either one will work, as long as I did my math right. It took like three times because the formula I don't remember off the top of my head, but it's you have a inverted exponential, and one is positive, and the other one is an inverted exponential minus. It might be swapped, and it ends up being quite ugly trying to solve for x. And the other way it was fun because I did so well in the other problems. And Catherine says, please like, share, subscribe. Thanks. Yes, I'm trying to get 1,000 subscribers, so I appreciate you helping with that. And we'll see if I can get there before the end of the year. So, but as we were talking about fermions and bosons getting to a certain energy level, at this point, this helium atom is at a stable position. This will be called a bond length. So remember that the x-axis is r, radius, the distance between them. So now, basically, you have this uh, bond length that's just perfect. It's not too long, it's not too short, where the protons are not pushing too hard away from each other. But at the same time, the electrons are happy because they can share these two protons, and they're happy. And, they could get attracted to this one and that one, and this can get attracted to both of them. Now each of them feel like they have two protons, and everybody's happy. So the energy is very low because everybody's nice and calm because everything is copacetic. It's not stressing either way, and that's our bond length. And they wanted us to. What else did he want us to do? So I described what happens to the energy. I described why the energy increases as R gets small. That's on this side. I also talked about when R gets big. That's pretty much the answer. He just wanted us to describe everything I described to y'all to show that we understand why bonds happen in the way they do. He also mentioned the direct and exchange term. I did mention that. Now, there's some other details that I'm forgetting about. Like, for instance, there's a well depth term, which I believe is here. As I mentioned here, how this is basically like a well problem, even though before we were just talking like a hypothetical particle in an infinite well. But now when you're putting particles near each other and they have charges, it really behaves like a well. So it's like this proton is a well and the other proton is a well. And these wells have a certain depth, just like how if you look at the planet Earth, it has a certain depth to its gravity well, right? It's going to pull something differently than if I was to put this orange in space. And both of these are going to pull differently than the sun, which is holding entire planets because the gravity wells are different. So my understanding is, if I remember properly, this uh, the depth of the energy indicates the well depth. So this will be an E quantity uh, from there to there. That's basically the energy needed to kick these protons out of this away from each other. You could say is even the bond energy. And so molecules, atoms have bond energy where it takes when they get closer and the energy goes down because they're so comfy with each other, it takes that much energy to boost them away from each other to break them apart. which is why we could extract so much energy from molecules and atoms when we break them up, like in an atom bomb, because when they're bonded together, they have this stored energy. This energy level goes down because it's so comfy. And when we break them apart, a lot of energy is released. And I might have that reverse. Maybe that's a fusion thing, but it's the same, along the same process, the same idea. These particles have certain energies when they get comfy with each other. The actor says, "I'm glad most of it went well, and I'm sure you'll be fine when you do get your results." Yeah, I think I will. But this quantum, I'm feeling a lot better about it. I've been working on it. Uh, I'm feeling better about it. So I've already calculated what I need to get a B, and calculate what I need to get an A. I think I'm going to try to get an A. Of course, I think I can do it, but it's going to be a long shot. I mean, I made an A on the first exam. I made a F on the second exam, but I knew that the final would overwrite the lowest thing, and I was focused on other classes at the time. But still, it is a trek. So, I mean, basically, this exam here will determine, do I get an A out the class? It seems most likely I'm in the BC range if I base it on the average of my last two exams. But I can pull it up, so we'll see how it goes. I think that's the last. Keep thinking there's one other thing. There's well depth. That's it. I don't know. I'm gonna have to look it up before tomorrow or about tomorrow. Me and the guy who came to my study group earlier today, he says that a few of the guys are going to meet again to tomorrow. So I want to make sure to get to bed early so I can one get some sleep because I was up all night last night. Some of y'all know I work as a well, I guess that job is ended as a learning assistant because the semester's ended. And I also work as a security person in the dorms, like a student security coordinator, and that's overnight. So once or twice a week, I'm up all night, and I just, sometimes it's very busy, but sometimes I get to get some studying in. So it was pretty busy last night, but I was able to get like an hour divided amongst the whole night. I was able to get like an hour or two of studying in, I would say, like 5 minutes here, 10 minutes there, 5 minutes there. I think I added up to a good hour, right, and then like maybe two. But I'm sleepy. It's all outdoors. So I only got took like a short nap, but I knew I had to study for the study group, and then I did a stream earlier, and then I studied some more for this stream, and uh, and then ate and other stuff. You still got to do that stuff. But I'm definitely going to get some sleep. So thanks all everybody who is watching. I'm going to go ahead and log off, get me some sleep, and go to the Terra Dome of my Quantum 2 exam. Wish me luck. And I feel, I mean, I already did the calculations. I mean, it's pretty certain I'm going to pass the class with at least a C. I mean, I'm fairly certain about that. I mean, I'm going to get I'm in the grad school. It's not like you can get into grad school and like make F's on everything and still go the same way. So I'm making sure I do well enough, as well as possible to keep a good high GPA. But at this point, it seems like, well, I know I have an A in relativity. It seems like I'm gonna get an A in my scientific apparatus class. Right now, I have A minus in thermal. I gotta wait for the exam grade to come in, which I think I did well on. So it looks like I have an A in thermal. My goal was to get an A in all classes. So if I can pull an A out of this exam, I think I only have to pull an A out. I don't remember what it was. I had to pull a C, I believe. If I get a C on this exam, because I did so well in everything else, I'll get an A out the class, a low A, but still an A. So if I can do that, then I will have succeeded at getting an A in this semester and graduating with an A, well, with an A minus. So if I do that, I'll graduate with an A minus, and if not, I'll probably graduate with a B plus, like, overall. So either one is still good, but I'll see. And I plan on actually taking a classics class to read the Odyssey over the summer for fun, which may be able to boost my grade a little bit, my GPA a little bit. And plus, I want to keep my momentum going with taking classes. Thanks for the well wishes, Catherine. And Catherine says, new background, cool. Oh, yes, let me tell you about the background. So, hold up, where did I put it at? Let's see here. So, what I need to do is go to the share screen, this share screen, and take off the pad. There we go. So in my model lab, one of the experiments I did was Frank Hertz, and this is one of the experiments that confirms the quantum nature of matter by it takes gas, neon gas, mercury gas. In this case, that's a neon, and it excites it with a potential. And what happens is it's a multi-phase potential. So there's a tube with the gas in there, and there's these different circuits, and the circuits accelerate the gas, and it accelerates, and you manually control the voltage. And you could accelerate it so fast that it gets to the point where it excites the neon to the next energy level, and then when it's excited, it emits that energy, and then you see the fluorescence. And when it emits that energy, it emits it after the first circuit. And then the next circuit accelerates it again, but only at certain energy levels does it excite and emit. So for one, you can control the voltage and show that it only excites and emits at very distinct energy levels. That's called quanta. So in quantum mechanics, we understand that like you can't spin something on a big level, it seems like you could spin something infinitely slow and smoothly. But at the quantum level, we know things move in jerks, like only certain amounts of energy, specific amounts of energy. So you can't just put like random amounts of energy in there and it slowly goes up. It has to be the exact amount of energy that it jumps up. And then it jumps down and spits out that exact amount of energy. And that's the fluorescence we see. So 3 times we were able to excite it and show every single time only when that voltage ramps up at that particular point to the exact energy does it excite and emit. And we're able to show that there's a quantum nature to subatomic particles. So that's a visual evidence of the quantum nature of matter. So that's what that is. So that's actually me taking a picture of the actual uh, 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 glass uh, window on the actual mechanism that's holding the neon gas and has all the device that's causing the electric movements. And of course, we're dealing with subatomic particles, so to us it seems very small, but to an electron or whatever, it's going a pretty good distance and picking up speed and picking up energy, and then when it gets enough, it hits and boom, it knocks an electron to a higher energy state when it once you get to that precise speed where that not matches that energy, and then it emits. We see it happen 3 times. Oh yeah, that was a fun experiment. I enjoyed it. Good visual representation, and I don't know if you can see the three. If you look at it, there's 3 distinct bands. You can see it's very bright pink at the bottom. It gets a little dim, then it gets bright again, and it's kind of hard to see the break at the top one. But it's always a pretty cool experiment. So yeah, I enjoyed that. And of course, it comes to mind the nonsense Catherine at the flat earthers talk about how they just believe. I happen to see Earth is Life had invited me to a Discord server. He invited me, and I joined I don't know, just to pop in because I got the invite. And there's people arguing about flat Earth, and I just left the server and I just mailed them and let them know, hey, I don't want to talk to these people anymore. But I happened to see him stream again on one of these Discord servers, and I just clicked the link just to listen, and you can hear the flat earther saying, "Yeah, they just believe it; it's just nonsense." And all of this is going on, and they just close their eyes and ears. It's just amazing. That's probably why I got into it. It's just the psychological aspect of it. It's just so amazing that people believe the nonsense they believe when the evidence is so everywhere and it's so easy to get. Um, but it's not hard. But if you came to my university and you say, "Hey, what are y'all doing? Can I hear about it? I'm just interested in science." And I was the learning assistant at that lab. I said, "Yeah, come in. Let me show you what tell you what we're talking about." It's just amazing, But I think I learned all I could as far as ecology. I mean, they are what they are. Uh, and now it just seems like a waste of time. Whenever I start to listen to them, I just can't do it for more than like a minute or two. For I just got to go actually watch a movie, even just do something where it's more worth my time. So but I still remember the psychological insights I gained by studying those people. So it's amazing. So awesome. Thank y'all for joining. Thank y'all for watching. Subscribe if you haven't already. I probably won't be streaming tomorrow, and I've had this flurry of streams preparing for exams, so I probably actually take a little bit of a break throughout the week. I definitely will be back on Saturday, which is hold up, I forgot. I graduate on Saturday. Hold up. Look at my calendar. The graduation ceremony is Saturday. What time is it? It is from 4 to 7. So I should be able to still stream. So I may be a bit late. But I actually have a graduation ceremony on Saturday. Provided all my exams go well, they're going well so far. So you're certainly welcome. And I'll see y'all Saturday on my other channel, that is. And by the way, everybody on this channel, I'll continue to stream on this channel as well. As you can see, it's a bit more in depth on this channel. It's a bit more direct, actually doing stuff here rather than giving an overview like I do on my other channel. So, and I've gotten a few messages either here on live chat or elsewhere letting me know you appreciate it. So I'll make sure to continue to be regular here. So you'll probably see me here once during the week. And then I'll be there for my regular Saturday stream on Saturday on the other channel. And thank you for your appreciation. And I'll see y'all next time.